In this video, I just want to go over the various things that we've learned about in this course and try to, in this very simple introductory course at least, and try to put some pieces together for everything that we've done and try to connect some concepts. So when we learned about the derivative, we basically tried to calculate it for various functions here, and you can see those functions here. And this is just a summary of everything that we learned when we basically tried to invoke the definition of the derivative in terms of limits and actually start calculating what the derivatives are for certain functions. And obviously we have the same thing for the integrals over here. We only did two on the integral side because it's a lot harder to calculate integrals. The reason that it's a lot harder to calculate integrals with the definition is basically because we have that summation term. So you remember the integral is the limit of the Riemann sums as n approaches infinity, as the number of partitions approaches infinity. So that summation term makes it a lot harder to calculate things, which is why we sort of left out these last three entries in the table. The derivative is actually a lot easier to calculate than the integral, which is why it's so much easier to calculate derivatives for various functions. And I just want to make a point. As we were going through and calculating derivatives and integrals, things were very difficult. So if you look at the timestamps on most of these videos, we're talking like 30 minutes to an hour possibly when you're starting at least to make sure you get everything right. That's a very long time to calculate derivatives, and you really don't want to be doing that. It would be a lot easier if we sort of created this table and remembered some quick tricks or some quick rules in order to help us calculate things faster. And that's sort of what the power rule is for. The power rule is used to basically calculate polynomials. So if you ever see a polynomial of any term, you can just sort of drop the degree down and subtract the degree one. So that's why we have this t. We drop the 2 down and decrease the degree by 1, and that's supposed to be a rule to speed things up. And then in the same way, we didn't go over this in this course, but there's also a rule for constants. So constants you can basically pull out of the derivative. So the derivative, you can basically just take the derivative of t, which would be 1, and then multiply it by the constant, which is why this is equal to c. So there are various rules that you're going to learn in a normal calculus course to try to make things, basically try to make your life simpler so that you never have to actually use the definition of a derivative and definition of the integral to calculate anything. I just wanted to show you how to use those with some basic functions so you could get an appreciation of one, that the information is not completely made up. Like the concept itself is very logical and it actually does make sense, even if you don't get that feel from your calculus course. And two, I wanted you to get an appreciation of how hard and time consuming it is, so that you're motivated to remember your derivatives, so that you never have to actually calculate one the hard way. So after watching this series of videos, you should basically at this point be begging, please just give me a table of derivatives to remember for various functions and let me just apply them when I need it. And that's basically what you'll get in a normal calculus course. So with that in mind, we really need to find some solution for these integrals because, like I said, it just gets so hard to calculate. Like with 3 and 4 and 5, we really can't calculate them in practice for most functions. It's just very difficult. So we'd really like some way around that. And so what I just want to do in this video is go over this table and see if we can kind of stumble on any patterns. And I'll just give you a hint. There is a very important pattern that lets you calculate integrals in a lot faster way than we've been calculating them for these functions. So I just want to go over that. Now, if we look at this and we basically stare at this for long enough, remember, we only have two samples that we're working with here, so I don't expect us to, if you don't come up with this idea, don't beat yourself up over it. It's not necessarily obvious, but there's definitely a similarity in these functions. So like for example, it's always like some function of b minus the same function of a. So for both of these, so when we calculated the derivative for the constant function c, we get this. That was true, and when we did it for this one, the linear function c times t, that was also true. So we wouldn't have expected beforehand that it would be like that, but it really does look like what we're looking at is some function. I don't know what I'll call it. I don't know, I just call it big F, I guess. And it looks like we're looking at some function of b minus that big same function of a for everything. That is what it looks like. It does appear to be that way. So yeah, like if you think here, what would the function be? It would basically be big F of t, whoops, of t equals basically c times t. So if you combine these and you say, all right, let's plug in b here, well then you get cb, which is the first term. That explains that. And then if you plug in f of a to this function, you get c times a. And if you subtract the two, you get what we actually determined experimentally. Or not experimentally, but by using the definition of the integral. If we look here, following that same logic where we have some function of b minus some function of a, where the functions are the same, we had no idea that it would pop out in this form. It's just that's what happened when we actually started calculating things with the definition of the derivative. What this one seems to be is basically f of t equals c over 2 times t squared. And obviously we don't know for the rest because we didn't calculate that far. But this is what we got so far. And the question is, is there any special shortcut we could use to, first off, let's assume that every integral that we ever calculate over some interval, every definite integral, I should introduce that terminology. A definite integral is an integral that's actually calculated over some interval a and b. So if you imagine, some arbitrary function a, b, actually doing what we did earlier over the interval to find the area under the curve, that would be called a definite integral. Whereas if we just sort of assume that every definite integral is going to follow this, this format, at least for all the equations that we want, our new job actually becomes, all right, if we could just find the f, if we could just find this some way to find this big F as a shortcut, we could actually calculate integrals a lot faster because we could just find this big F, plug in b, and then whatever the, whatever that is. So let's say this is little f of t, and we do that, and we just basically take big F, evaluate it at b, and we take big F, evaluated at a, and that would actually be a quick way to calculate the derivatives or the integrals or the areas under the curve. So let's just assume that. Now I haven't proven that. It's going to be too hard to prove that. It has been proved, so it is true. It is true, but I don't want to get into that because it's just going to be too complicated for a course like this. But let me just tell you that this pattern does hold for all the integrals that you would ever calculate. All the functions that you would ever be interested in finding the integral for, everything that's an integrable or continuous function, it does follow this pattern. So this is actually called the second fundamental theorem of calculus. This right here. The first fundamental theorem of calculus then has to do with finding this function f, because remember, if this is true for all the integrals we want, then our new job is just find this big F for it. So whenever we're given a function like this, we just want to be able to find this big function, or this larger function f, and if we do that, then we'll be able to calculate the integrals efficiently. So looking at this pattern here, so let's see if we can compare these f's. Let's see if we can compare things in this column to the original functions and see if there's any connections. So here, if this one is ct, do we see anything with ct over here? Actually, we do. It looks like this one. So it's not the derivative, it's not the derivative of this function, but it's almost like the derivative of ct is equal to the integral of c. That's what we're looking at here. So we're basically seeing this function, this f of t, and how that's related to this function. They're the same. Let's try that again. If we go here for a polynomial, we have c over 2 t squared, and if we look at that, well, the reason, so this is almost the same. So we have c times t squared. It's just that we have this half term here. Why is that? Well, if you look here, if you're taking the derivative of this, you actually get this 2 out in front. So the derivative that we're talking about is not, for this one, is ct, not 2ct, which explains why we have this extra half term here. So if No, we've only done it for 2, and we haven't proved it, but I will tell you that it is actually true. So in other words, let me try to scroll down and try to spell it out a little bit more clearly in case you're not following. If we want to find, let's say we have some arbitrary function f of t, and we want to find the integral of that from on the interval a to b over dt, which has a physical meaning, then what this is saying is that this is going to be equal to some function f of b minus f of a. And now, obviously, we still can't calculate it. We still need to know what this f is. The answer, what this is saying is that, how should I put this? The derivative of f t is equal to this. So in other words, if we have this f of t over here, and we take the derivative of this, remember we know how to take the derivatives with the power rule. You just take this 2, drop it in front, and then decrease the power by 1, what will you be left with? So let's just say, for example, we're talking about this function here. So if we have f of t equals c over 2 of t squared, and we want to take the derivative of that, what is that going to equal? Well, drop the 2 down, so we'll have 2 over 2 c, and then decrease the power by 1. That's the power rule. So we're left with ct. Well, ct is the original function that we wanted to integrate over here. So hopefully you can see how this is matching up. We have this function f of t, which is this left column here, and in order to actually calculate the integral over some interval, we can use this equation. And in order to find what this function is, to actually evaluate it at the endpoints, we actually just take the derivative of this, and that should equal this. So in other words, it's almost like the opposite of the derivative. So in order to find this function f that we should use, it's almost like we take the opposite of the derivative. So let me just run with this idea a little bit more, just to kind of hit the idea home. But if we're talking, so let's just say we're talking about f of t equals, I don't know, let's just do what we've been doing. So c of t, and we say we want to find the integral of b over a of this function, the area under the curve of this function. Well, that is going to equal, according to this, it's going to equal f of b minus big F of a, where f is sort of the opposite of the power rule. So if you think of this as, if you think of, or whoops, sorry about that. If you think of, c times t to the 1, we know the power rule tells us that we should bring the power down and then basically decrease the power by 1. But here we should actually do the opposite of the power rule, basically do the power rule backwards. So we're actually going to increase the degree by 1, so t squared, and we're basically going to pull a 2 out front. So there is no 2 out front right now, but you can sort of imagine one there. And if we, 2 over 2 is 1, which is why we have a 1 times here. So this is actually let me do an intermediate step here. So let's just say that I rewrite it like this, and you can see that. And then what this is actually saying is you take basically the opposite of the derivative, basically do the derivative backwards, so that you'll be left with, t squared 1/2 c. So we're taking, and it's actually called, the anti-derivative. So, and we're basically using the power rule here. And now if you go back here, you want to go backwards, use the derivative. So we take the 2, we drop it out in front. We'll have 2 over 2, which cancels out to 1. And then we'll have c, because that's a constant, and we'll be left with t. So basically what this is saying is that, f of t is anti-derivative of little f of t. So if you give me any f, so if you're given a little f of t and you want to find the antiderivative, it's basically you got to find the function f, big F of t, such that the derivative of big F of t is little f, and that's basically It's basically what's represented up here. So this is actually the first and fundamental theorems of calculus, and you can see that we stumble on them just by actually trying to calculate integrals with the definitions of integrals based on basically that they're the limits of Riemann sums as the number of partitions approaches infinity. Just running with that definition, this pattern sort of pops out. And like I said, we haven't proved it. It's very hard to prove actually, and it's pretty dense. It's not very intuitive, the proof, but you can definitely see how this concept is popping up. So just to summarize what we learned, the first fundamental theorem. And every branch of math, by the way, has its own fundamental theorem. There's a fundamental theorem of algebra, calculus. It's sort of like the most important thing in the field, or in the subfield at least. First fundamental theorem is if it's basically that if we have some function f of t and we're trying to integrate b over a of f of t times dt, then antiderivative f of t is function, or whoops, is the function that we'll need. And f prime of t is f of t. So that's how you can actually find it. You need to find the function such that if you find the derivative of that function, you'll get this. And it's basically what you'll use some of the various derivatives that you learn in a calculus class, and you'll use them in reverse. So that's basically the trick. You use them in reverse. And then the second fundamental theorem is that if you want to calculate this, and actually I should actually change this, because what you use, this is actually called an indefinite integral. It's basically where we take away the bounds. Now, if you take away the bounds, it doesn't actually make sense. You can't calculate it, but we basically assume, just to make things more logical, that the something called the indefinite integral. So if I actually make some room on that, so just continuing down here, so it's something called the indefinite integral here. We say it's actually equal to f of t. Now that's not actually true. That doesn't make sense, but thinking about the first fundamental theorem this way does actually make sense. And if you basically take the derivative of this, like we said up here, the derivative of big F is equal to little f. So you can almost, if you look at it through this lens, it almost looks like the derivative and the integral are sort of inverse operations. So if you take the integral of little f, the indefinite integral at least, then you'll get big F. And if you take the derivative of big F, you get little f, what you started with. So in other words, if you take the, let's say you have the integral of f of t dt, and you take the whole thing, the derivative of the whole thing with respect to t, it'll actually spit out f of t. So this is basically what the first fundamental theorem is getting at. It's basically that the derivative and the integral are, in one sense, inverse operations. So that's a slight that's a slight fudge on the numbers, because, like I said, you actually need a certain a and b to evaluate them at the endpoint. But that's basically what the second fundamental theorem covers, and it basically says, let me rewrite that a bit. That basically says that the way you actually evaluate it is by taking the antiderivative at the endpoints. So these are sort of the two sides of the same coin. They're basically, you could kind of forget about both of them if you want, and you could just actually calculate the derivatives like we've been calculating them. That'll take a ton of time and effort, and you might make a lot of mistakes, but if you do it right, then you will get the right answers. It's just that you'll start to see this pattern over and over, and it sort of makes sense to look at things through this new lens. Because if you look at them through the new lens, then you can actually calculate the integrals a lot faster. All you have to do is really, really be good at your derivative tables and basically know all the derivative rules, the power rule, the trigonometric derivatives, the logarithm derivatives, all that stuff. And if you're really good with all that stuff, then you can actually just sort of use those rules as a shortcut to find these antiderivatives. And then you can use the second fundamental theorem of calculus to just sort of plug in the endpoints into this equation and calculate stuff. So for example, let's say, just we haven't really done any hard numbers throughout this entire time that we've been calculating integrals, but just, if we want to say, let's say we have the equation, t3 times 7, and I want to find the integral of it from, I don't know, 4 to 8, dt. What does that represent? That represents basically, let's say we have the 7t of 3, that's going to look like a function like this, and I'm trying to find this area under the curve here for some arbitrary function. If I just use the first and second fundamental theorems of calculus, that's basically going to say, okay, first thing I need to do is take the antiderivative of this. Now this is just a normal polynomial, so we can use the power rule, but we got to use the opposite of the power rule. So instead of taking this 3 and dropping it down and decreasing it, we'll do those steps in reverse. We'll basically first we'll increase that. So we'll increase that, and then we'll basically pull out the constant out of the denominator. And if you don't believe me, if you don't believe that 7/4 t to the fourth power is actually the antiderivative of this, then I would encourage you to actually just take the derivative of this with the power rule. So take this 4, drop it down into the numerator, so you'll have 4 over 4, which cancel out, leave you a 7, and then you drop it, and you get t to the third. So going in this direction, if you take the derivative of this, you actually do get this. So this is the antiderivative. And then we introduce this new notation, 8/4, which basically means that you have 7/4 over 8 to the fourth minus 7/4 over 4 to the fourth. So this is the f of b. So 8 is b in this case. 8 is the end of the integral, the b that we've been working with this whole time, and then a would be 4 in this specific example. And you can actually calculate this, and you'll notice these are all numbers. So you can actually type that into a calculator and get a number, and that number represents the actual area under this curve. So this is actually the strength of calculus. If you build up a lot of derivative rules, and then you keep in mind the first and second fundamental theorems of calculus, and you're able to find antiderivatives, because you remember your derivative tables well and your derivative rules, and you're able to remember to evaluate at the endpoints using this formula, we actually calculated this extremely quickly. Think about how big of a pain it would have been if we actually used the actual full limit, or if we actually used the full definition of an integral like we've been doing. If we did, n, to the infinity as I equals 1 to n of, what would that be? That would be 7 times or I guess it would be 7 times 4 plus delta t. So delta t would be 4 over n. That's b minus a, 8 minus 4. Remember, delta t equals b minus a over n. So delta t in this case would be 8 minus 4 over n, or 4 over n. So plus 4 over n times I times 4 over n. I mean, we could just do this. That's actually the definition of the integral, but that'd be a huge headache. Oh, and I'm sorry, it's actually even harder than that because we have this cube here. This cube is what really makes it hard. So, think about that. So now we're talking about, finding summations for I cubed, where we only had to do it before for I. That's going to be a lot harder, and it's going to take you realistically, it'll probably take you a half hour to 45 minutes to calculate it this way. Whereas if you remember these special tricks, the first and second fundamental theorems, well, and assuming you're good at your derivatives, your power rule, you remember the power rule and you know how to do the opposite of the power rule, the kind of antiderivative power rule, well, then you can solve it in about, I don't know, a minute and a half. So that's sort of the value of this. So when you're going through your calculus course and they give you all these tables and you say, oh, I got to remember all these numbers, just think what the alternative is. The alternative is far worse. So basically, I guess, be thankful for the tables and know that the tables are just they're not made up. They're not just handed down from above. Like they actually do make sense logically. They're just generalizations of these more complicated definitions, and that's sort of the main takeaway I want you to have from this course. It's just I just want this course to be a supplement to all of the specific rules that you learn in a normal calculus course. So I hope you enjoyed it.